Hello students and welcome. Today, we're going to tackle a very important topic from our nuclei chapter, the size of the nucleus. I know it can sound a bit complicated, but trust me, it's the key to understanding everything else in this unit. So don't you worry, I'm going to make it super simple and completely exam safe for you.
So here's our plan for today. First, we'll get a real feel for just how tiny a nucleus actually is. Then we'll learn the main rule for its size, try a quick calculation, and I'll show you a very common mistake you absolutely have to avoid. After that, we'll see why this whole idea is so important, and we'll finish up with a quick revision. Let's get started.
Okay, so let's jump right in. Before we even look at any formulas, let's first get a picture in our minds of the scale we are talking about here. It's kind of mind-blowing.
So let me just ask you this. Just how small is the nucleus? I mean, we all know it's small, but can you really imagine its size compared to the whole atom? Well, your NCERT textbook gives a brilliant way to think about this. Just imagine that your classroom is one single atom. If the whole room is the atom, then the nucleus would be like a tiny pinhead placed right in the center. The rest of that huge classroom, that's just empty space where the electrons are moving around.
But here's the truly shocking part. That tiny pinhead in the middle of our classroom. It contains more than 99.9% of the atom's entire mass. Just think about that. Almost all the weight is packed into that unbelievably small space.
So how do physicists even know this? Well, they don't just guess these things, of course. There is actually a very specific and, thankfully, a very simple rule that helps us calculate the size of any nucleus we want.
To understand this rule, just think of the nucleus as a ball made of marbles all stuck together. Each marble is either a proton or a neutron. It's simple logic, nah? The more marbles you add to the collection, the bigger the ball is going to get.
And that very simple idea leads us directly to the main formula you need to know. This is straight from your textbook, and you absolutely must remember it for your exams. It says the radius of the nucleus, r, is equal to a constant, r0, which we call r0, multiplied by a to the power of 1/3. And you know that's just the cube root of it.
Okay, let's break this down. R is the nuclear radius we want to find. A is the mass number, which is just the total count of protons and neutrons. Basically, it's our total number of marbles. And R0, or R0, is just a constant number. Its value is approximately 1.2 times 10 to the power of minus 15 meters, which is also called 1.2 femtometers. You should definitely remember this value.
Now that we have the theory, let's actually put it to use. We'll solve a simple exam-style problem together to see how this formula really works.
All right, here's our question. It's very similar to one in your NCERT exercises. We need to find the approximate ratio of the nuclear radii of gold 197 and silver 107.
Okay, let's walk through this step by step. First, we remember our formula. Second, because the question asked for a ratio, we set it up as the radius of gold divided by the radius of silver. Third, we just substitute the formula for both. Now, here's the beautiful part. In step 4, you can see that the constant R0 is on the top and the bottom, so it just cancels out. This makes our calculation so much simpler. For step 5, we just put in the mass numbers, 197 for gold, 107 for silver. And finally, we calculate the cube root of that ratio, which gives us an answer of approximately 1.23. See? It's that simple.
Okay, now I need your full attention for a minute. I want to talk about a very common trap, a misconception that I like to call the silent killer, because it can quietly make you lose marks in your exam.
So the common mistake is to think that a bigger, heavier nucleus like gold must be more spread out, and so it must be less dense. I know it kind of feels logical, but it is completely wrong. The correct idea, the fact that will save you marks, is this. All nuclei have almost the exact same unbelievably high density.
So why is this true? Well, the logic is hiding right there in our formula. We know the volume of a sphere is proportional to its radius cubed, right? So if we cube our radius formula, we see that r cubed is proportional to the mass number, a. Now the mass of the nucleus is also proportional to a. So what does that mean? It means as the mass increases, the volume increases in the exact same proportion. And the ratio of mass to volume, well, that's density, and it stays constant for all nuclei.
Now, you might be wondering, Sir, why are we spending so much time on this one small formula? Well, it's because understanding the size of the nucleus is the key that unlocks the rest of nuclear physics for you.
Just think about the connections. The size of the nucleus helps us understand the range of the strong nuclear force. It explains why really big nuclei become unstable and radioactive. You simply can't understand the concept of binding energy without it. And it's the starting point for all calculations on nuclear fission and fusion. You see, it's connected to everything that's coming next in this chapter.
Okay, before we finish, let's do a very quick revision of the most important points from today. These are the absolute must-know facts for your exam.
First, the formula is R equals R naught times A to the power 1 by 3. Second, the constant R naught is about 1.2 femtometers. Third, the nucleus is roughly 10,000 times smaller than the atom. And fourth, our most important takeaway today, the density of all nuclear matter is constant and incredibly high. Please don't forget this last point.
And I'll leave you with a final thought to think about. If all nuclei, from the lightest hydrogen to the heaviest uranium, are all made of the same stuff, and they're all packed to the exact same density, what does that tell us about the fundamental nature of nuclear matter itself? It's a deep question. Think about it. That's all for today. See you in the next class.